Hello, I'm Mike Cinkoske, and today I'm going to talk about a new connection between node and edge depth of bus graphs. This is joint work with Jeremiah Blocki. A depth of bus graph is a directed acyclic graph that has certain properties that we'll define on the next slide. The reason we're interested in depth of bus graphs is they have many applications to cryptography. Possibly the biggest application is depth of bus graphs are used to create secure, data-independent memory hard functions, which are used for password hashing. Additionally, depth of bus graphs have applications to proofs of space and proofs of sequential work. So to define depth of bus graphs, we'll first define maybe a simpler related notion. We'll say if G is a directed acyclic graph, then we say G is ED node reducible if there's some set of vertices of size at most E, such that when we remove all those vertices, the depth of the remaining graph is less than or equal to D. And then we'll say that G is ED node depth of bust if it's not ED node reducible. And so as an example, we have this graph here, and if we just say remove node 2, then the depth of the graph is 3. So we say that this graph would be 1, 3 node reducible. And node depth of bust would just be, not node reducible. And similarly, so traditionally when we say depth robustness without qualifying it, we mean no depth robustness. But in this talk, we'll be talking about both edge and node depth robustness, so I will tend to qualify it. And so analogously, we can define edge depth of bus graphs, where here or edge reducible graphs where we just remove a set of edges in this case. So we remove edges instead of nodes. So here again, we have this graph, and we can just remove the edge from 1 to 2, and we see that if we remove one edge, then the depth of the remaining graph would just be 4. So this graph would be 1, 4 edge reducible. And so I guess the reason that we're interested in comparing node and edge depth of bus graphs is edge depth of bus graphs are potentially easier to construct than node depth of bus graphs. If you think about just removing a single edge from a graph doesn't affect it as much as, say, removing a node and then potentially removing all of the edges incident to it. And so, for example, we have two well-known constructions of depth of bus graphs. The Erdős-Gram-Simrity graph, which is no depth of bus graph, but it has a very complicated construction and analysis. On the other hand, there's the Graetz construction that is edge depth of bust, but has a simple construction and a simple analysis. And furthermore, many applications require no depth of bus graphs. In fact, all the applications I mentioned earlier, memory hard functions, proofs of space, etc., all require no depth of bus graphs. So we want to construct no depth of bus graphs, but it's potentially harder to construct them than edge depth of bus graphs. So the results from our research is we come up with a transformation that transforms an ED edge depth of bus graph that has M edges into an E/2, D node depth of bus graph that has constant integrity and order M nodes. And as a specific example, if you apply it to the Graetz construction, we get a node depth of bus graph that has certain parameters here, and no other construction is known to achieve these specific parameters. And later in the talk, we'll get to why these specific parameters are important. But yes, ours is the first known example of these that has these parameters. Additionally, to actually construct this transformation, we define and then construct graphs that have a new connective property that we call ST robustness. These will get in the talk, we'll get into how we actually construct them, but these ST robust graphs also have applications to what we call perfectly tight proofs of space and constructing source distinct depth robust graphs that were used for wide block labeling functions proposed by Chen and Tazara. So first I'll go through our transformation at a very high level. So we take a highly edge depth of bus graph, G, and then we replace each node of G with an S-tier bus graph that has constant integrity. We have size proportional to the maximum of the in degree and out degree of the node. And then the resulting graph, the transformed graph, will have constant integrity and will be highly node depth of bus. So the question that we'll answer is, what properties should this added S-tier bus graph have? So we can translate between edge depth of busness and node depth of busness. So just as a pictorial example, say we have part of some graph here, and our transformation would just replace each of these nodes with a graph, with an S-tier bus graph. So the key building block, what we call a K1, K2 S-tier bus graph. So the graph is a directed acyclic graph that has n inputs and n outputs. So here are the inputs on the left side of this graph and outputs on the right side. And say we call out this graph K1, K2 S-tier bus if we can remove K1 nodes here in red, and there exists some subgraph of G where that has at least K2 inputs and K2 of the outputs, such that each input is connected to every single output. So for each input, there's a path from it to all of the outputs. These paths don't have to be node or edge disjoint or anything. They can overlap. It just has to, each input node has to be able to reach all of the outputs. So here, as an example, we have this graph, and we see that if we can remove any node, like any one node in this graph, and there'll always be some subgraph that has two inputs and two outputs, such that each input connects to all of the outputs. So we call it 1, 2, ST robust. So now what we'd like to construct is what we call maximal S-tier bus graphs. And we say that a directed acyclic graph G is maximally S-tier robust if it's K, n minus K S-tier robust for all K. And basically, we could potentially remove an output or input node because we can remove any of the nodes in the graph. So K, n minus K is the best possible parameters. And one of the main contributions of our paper is we prove the theorem and we construct a family of linear sized constant integrity maximally S-tier bus graphs. And by linear size, just mean that there's n inputs, then there'd be O of n nodes in the graph. So the core of our maximal S-tier bus construction consists of 3 copies of a highly node depth robust graph that has constant integrity. That we call, say, H1n, H2n, and H3n. And for each node in H3n, we pick, say, tau random parents in H2n. And tau is just a parameter that we can adjust, but it's a constant. So, And again, for in H2, we pick tau random parents in H1. So every node in H3 has some number of random parents in H2, and every node in H2 has some random parents in H1. And so we'd like to prove that, say, most of the nodes in H1 can reach, or most of the nodes in H3. And so the way we do this is we fix some set of nodes in the graph to remove, and then we know that each subgraph, H1, H2, and H3 is highly node depth robust. And so from the exact parameters, we can say find a long path in the graph and then remove it. And since it's depth robust, then we can do that multiple times and find a number of node disjoint paths. So for example, here on the right, say maybe the two graphs would be H2 and H3. Then H2 has some number of vertex disjoint paths, and H3 has some number of vertex disjoint paths. And we argue that, say, the upper half of the paths in the left graph, or each upper path in the left graph, connects to most of the lower paths in the right graphs. And by lower, we mean like the lower half, so the last half of the nodes. And we do that for both pairs, so H1 and H2, and then H2 and H3. And then after that, we union bound over all possible S's. And what we're proving is that most of the paths in H1 connect to or can reach most of the paths in H3. And finally, we attach these graphs called superconcentrators to H1 and H2. We don't really have time to go into and define another graph, but basically they just ensure connectivity between all pairs of inputs and outputs in the final ST robust construction. And furthermore, just to note that this graph by itself is not maximally ST robust. It is K1 and K2 ST robust for certain parameters, but we have another construction that you can use to bootstrap into a maximal ST robust graph, but just won't go into it here. And so here is the formal statement of our main theorem. So if we have a DAG G that with M edges, that is E comma D edge depth robust, and we have a family of maximally ST robust graphs that have constant in degree, then the transform graph G prime will be E over 2 comma D depth robust. And I'll have max in degree is just the max in degree of any of the ST robust graphs. And then, which would just be the, which would be constant if family of ST robust graphs has constant in degree. And then we'll have a linear number of nodes. You just add up the number of nodes in each of the ST robust graphs. And so the way we prove the main theorem is basically by relying on the ST robustness property. So here we're looking at, say, one node in the graph that's been replaced by an ST robust graph that has 3 incoming edges and 2 edges connected to the output nodes. And so say we remove one node from this graph. So we're removing, say, one node from the ST robust graph. Then by the ST robustness property, we know there's a subgraph that has 2 input nodes and 2 output nodes, such that each input node connects to all the output nodes. And so what this corresponds to is, it's like we're removing 2 edges, the edges in red here, it's like we're removing these 2 edges from the original graph. And that's because we can no longer guarantee that the each of the input red edge connects to all of the outgoing edges. And so by this S-tier robustness property, we see that removing a node in our transform graph corresponds to removing at most 2 edges in the original graph. And that's the reason that our transform graph is E over 2, comma D instead of just E, because we potentially lose 2 edges. And so, now that we see that we lose at most 2 edges, if we take our transform graph and remove a bunch of nodes, then that's equivalent to removing a bunch of edges from the original graph. And since the original graph was edge depth robust, there'll be some path through it. And then we can just transform that into a path in the transform graph, because by the S-tier robustness property, each of the input nodes connects to all of the output nodes. So we can just directly translate a path in the edge from the original graph into a path in the transform graph, as you can kind of see by this picture. And so that's kind of a intuitive, high-level overview of the proof of the main theorem. So sort of a guiding open question for why we're interested in these. There's a well-known lemma called Valiant's lemma that basically gives an upper bound on the max edge depth robustness of any DAG. So if you have a DAG G with M edges and N nodes, then that DAG would be M times I over log N, comma, N to the I edge reducible for all integers from 1 to log N. And the implication is for the constant integrity graphs that we're generally interested in applications, that means that they're some order of N times I over log N, comma, N over 2 to the I node reducible. And so sort of a guiding open question is, can we construct DAGs that match the bound for any given I? And so if we apply our transformation to the grades construction, then it gives us a N times I over log N, comma, N over log N to the I plus 1 node depth robust graph for all I from 1 to log N. And this is an improvement for I that are greater than 1 and less than log N. For I that are of order of 1 or order of log N, there's already known constructions that match it. But this is an improvement for the area in between those two. Specifically, we're interested in constructing a family of DAGs that would match the bound for I equals order of log N. And the reason that is, it would resolve open questions about the pebbling complexity of certain data-independent memory hard functions. In fact, it would could be used to construct maximally memory hard data-independent memory hard functions. But so our reduction would give N log N over log N, comma, N over log N to the 1 plus log N. So it doesn't match the bound because there's an extra log N to the log N in the denominator of D, but no other construction is known to achieve these parameters, specifically for that E that high of D. And in addition to just constructing depth robust graphs, S-tier robust graphs may be of independent interest because they have other applications. So for example, we can use an S-tier robust graph to construct a perfectly tight proof of space. So here on the right, we have a construction where we take a maximal S-tier robust graph, Mn, and then overlay a depth robust graph over the inputs. And then the red nodes would be the target nodes. So in the proof of space, a prover commits to store labels of n output nodes, which would be the target nodes colored red. in the picture. And in this case, we would use a maximal S-tier bus graph that has n prime inputs and outputs, where n prime is O of n log n. And then we overlay on the inputs an n comma order of n prime dr graph. And so the prover will commit to store these labels that are labels of the n output nodes. And a cheater will, say, store less than n nodes, so k for k less than n. And for each of the n minus k challenges that the cheater doesn't store, if the cheater is asked to produce that label by the verifier, then the cheater would have to repebble at least n prime minus k inputs by the ST robustness property. And that would take at least or omega n prime time. And so by tight proof of space, we mean that every challenge or every node that the cheater doesn't store forces the cheater to completely any node that the cheater doesn't store requires a lot of time, the full amount of omega n prime time to repebble. And finally, our S-tier bus graphs are actually what we call source to sink depth of bus graphs. And what that means is that we guarantee that the path of length d starts at a source node and ends at a sink node, or starts at one of the input nodes and ends at one of the output nodes. And these were used in the cited paper to construct something called wide block labeling functions. We won't get into the details, but our graphs are asymptotic improvements on the construction in their paper. So to summarize, we constructed a new reduction that transforms edge depth of bus graphs into node depth of bus graphs. And our reduction improves node depth of bus constructions for certain parameters. In order to create this transformation, we defined and constructed S-tier bus graphs. And these S-tier bus graphs also have applications to proof of space and to source to sink depth of bus graphs. And here's the references. And yeah, that's it. Thank you for listening.